Nuclear energy now produces 10% of the world's electricity, which is the second largest low-carbon power source in the world. It has been the subject of much public interest since its development in the mid-20th century, and has been touted as the fuel of the future for its very high energy conversion and small carbon footprint. All current nuclear plants use fission or separation of large atoms to generate energy. Uranium is currently the top choice for nuclear fusion because it is relatively easy to separate. It is highly abundant in nature, being 100 times more common than silver. 1 kilogram of uranium contains the same amount of energy as 126 gallons of oil, 1 ton of coal, or 17,000 cubic feet of natural gas. There are two common uranium isotopes, uranium-235 and uranium-238. Uranium-235 is the isotope most desired in nuclear power plants, but most natural uranium exists as uranium-238 at 99.3%, while the desired uranium-235 makes up only about 0.7%. Reactors actually require higher concentrations of uranium-235, around 3 to 20%, and nuclear weapons require up to 90% concentration. Hence, the necessity of an enrichment process to get to that higher concentration. The production of uranium is done in 4 general steps. First is we mine the uranium ore from underground. The depth, of course, depends on the location of the ore. Second, we treat that ore via crushing to turn the rock into smaller particles. And heating to remove carbon from the ore. Third, we then extract the uranium by leaching. This is the first separation stage. The leaching can either be in acid or in base, but we'll elaborate more on that later. By this point, we now have uranium complexes that are processed in our next stage. Fourth, we then purify, precipitate, and refine our uranium. In this stage, we convert the uranium complexes to what we may recall from the movies as yellow cake, which consists of U3O8 or triuranium octoxide. After more conversions, we end up with gaseous UF6 or uranium hexafluoride, which is fed to a centrifuge for the separation of the isotopes. This is the second important separation process, which we will elaborate more on later. By the end of this process, we have produced highly concentrated uranium-235 for energy or weapons use. Let's now explore the specifics of our separation processes. First, let's talk about leaching. There are two types of leaching, the first of which is acid leaching. Generally, we want to separate the uranium from the ore, so we convert the uranium to a soluble form. For acid leaching, we use manganese oxide, sodium chlorate, and ferrous salts to oxidize the uranium into uranyl sulfate. Here is the reaction pathway in case you're interested. The reaction occurs at around 60 degrees Celsius and will release H2, H2S, and CO2 gases as byproducts. This uranyl sulfate complex is highly soluble in sulfuric acid, and so in the leaching stage, the sulfuric acid dissolves the complex and leaves behind the other components of the ore. In the process, the uranium is converted from a tetravalent to a hexavalent state. But why hexavalent? It's because we will be converting our uranium to UF6, a hexavalent gas, in a later stage of our process. So what makes acid leaching a viable choice? Well, acid leaching requires only low temperatures and short leaching times. It also requires less pretreatment because acid leaching can work even if the particles weren't crushed beforehand. Acid leaching is actually also called heap leaching because it can be done on large heaps of uranium ore. Hence, acid leaching would require fewer and less complicated equipment and would drive down capital and operating costs. It is also an effective method for dealing with difficult ores that cannot be leached by the alkaline method. It is also possible to use nitric and hydrochloric acid because they can better oxidize the uranium, but are not common since they are more expensive and more corrosive than sulfur.
The second type of leaching is alkaline leaching. Again, we convert our uranium ore into a soluble form, which in this case is uranyl tricarbonate. This is done by bubbling with molecular oxygen, or O2, and mixing with sodium carbonate. Here's the reaction mechanism, just in case you're interested. Our leaching agents are sodium bicarbonate and sodium carbonate, which also serve the dual purpose of preventing the formation of undesired uranyl hydroxide. So, what makes alkaline leaching attractive? Well, alkaline leaching is highly selective to uranium minerals, so the products produced have fewer impurities. The desired yellow cake, as it is called, can actually be produced without the need for further refining. The alkaline solutions are also less corrosive and can easily be recycled. There are downsides, though, associated with this method. It generally requires higher operating temperatures, around 60 to 100 degrees Celsius, and pressures, as well as longer leaching times. The particle size must also be small, with 70 to 80% passing through 200 mesh. Thus, cyclones and ball mills might be needed to reduce the particle size. These drive up the equipment costs. Overall, alkaline leaching can be 10 to 20% more expensive than acid leaching. It is also possible to use other chemical oxidants, but economics dictates that oxygen from the air is the most sensible and viable choice. The other important separation process is the centrifuge. We take advantage of the mass difference between the isotopes U235 and U238 to separate them mechanically, and the most efficient option is by using a gas centrifuge. Prior to this, we convert the uranium complexes to yellow cake, which consists of U308 or triuranium octoxide. We then convert this to uranium dioxide or UO2, which is then treated with hydrogen fluoride to produce UF4 or uranium tetrafluoride. This is then reacted with fluoride gas to produce the gaseous UF6 or uranium hexafluoride, which is actually the hexavalent form we made earlier, and can now be placed in the centrifuge. The centrifuge is rotated at 50,000 to 70,000 RPM. The movement of the gas causes the heavier particles, or the U238 isotopes, to collect near the walls, and the lighter particles, the U235, to collect near the center. The central mixture with high amounts of U235 can now be extracted and converted to solid nuclear fuel. This is an incredibly energy-efficient process compared to other physical methods, and requires a small physical footprint. So to recap, uranium fuel is highly popular as an energy source for nuclear fission. It is extracted from underground deposits, hence the need of an extraction process, specifically a leaching stage. There are two types of leaching, acid and alkaline leaching. Acid leaching is generally cheaper, while alkaline leaching produces a much purer product. Of the two uranium isotopes, we mainly desire U235, hence the need for an isotope separation step, which is most commonly a centrifuge.